Okay, we'll give people a few minutes. There's always some late comers to this one. How are you guys going with the report?
I don't know.
Submission tonight, right?
Yeah.
I'm going to give a slide on some tips, okay? Last minute advice.
And there are also conflicts between the PDF file and the doc file.
Which
Difference.
in which files?
In the doc file IEA, they told us we have to have a requirements summary, something. But in the PDF file, things you need to check. There's not requirements and summary.
Okay, well, so one of them is a template, right? Some people are interpreting the template a bit too literally, like it's just a guideline, okay? I don't think there's any strict format. That's just some example for you. But I'll check those, because Binesh put those up. I'll double check them. But yeah, don't feel like you have to follow the template perfectly. It's really just to show you the important things about structuring, make sure you caption figures, make sure you have a reference correctly, that you do have sections instead of just a big load of text.
Do we have to capture every picture? Do we have to take a photo of every evidence?
No. Not for this. Just you be selective on what you think is important. Yeah, because only 3 pages. I know you can't fit everything in, and that's part of the work, right? So we'll give them a few more minutes. Is there any event on today? Is there any other conflicting class you know about? Just the usual late? Yeah. Okay. Normally more people have made it here by now. Hello. Okay, it's 10 past, so we'll get started. Hopefully a few more people will show up. I can always go back to those slides. So today we're going to be talking about power amplifiers. So it's the first lecture on power amps. I'm going to cover a few other things as well. At the beginning we just talk about some of the previous assignments, a few tips for the report writing. I know it's a bit last minute. And also introduce you to the next lab, which is going to be quite different to the previous labs. So we're trying some new stuff there, which I'll talk about a little bit at the end. So first, I don't think Binesh got a chance to show you the assignment 2 results. So this was a while back, the differential amplifiers assignment. So this is the topic I taught before the session break. So just to see the spread of results, you can see the average very high, 78.65. So that's a great result for that. A lot of people in the 95 to 100, so a lot of people getting full marks. And that's great to see. Maybe indicates I need to add a few harder questions. But I'm sure you're not complaining if getting high marks. So look at where you sit on that curve. If you're in the lower half, certainly if you're on this assignment getting less than 60, then it means differential amplifiers is a topic you might want to focus on. If you're in the right half, especially if you're one of the, I think 21 students have got 100%, then you're doing great. And differential amplifiers, you can just go over these questions again for your exam revision, and I think you'll be fine. So for everyone that just walked in, that's just the assignment summary results for assignment 2. You're still doing assignment 3. That's correct, right? So yeah, very good results all around. So well done. So just a quick poll to check how confident you're feeling. Again, I know this was a little while ago that we did differential amplifiers, but you are doing the report on it now. So if you can go to the website there, it's at the top of the screen, polev.com/David Payne 187, and just give me an idea of this. We can use this, for example, you know, you have a couple of review lectures at the end of the session, so we can look back at these and see where people were struggling, and we'll focus more on those topics for the review. So I'll just give you a couple of minutes to log in and cast a vote there. All right, so far everybody's reasonably confident. Anybody need more time? All good? Okay, that's great. So just going to go over some of the upcoming assessment tasks. So this is just a reminder, lab report 1 due tonight. I think midnight the system will cut you off. It will be late submissions after that. As I said to the people here early, I'm going to give a few tips on the report writing in the next few slides. Assignment 3, nonlinearity and mixers, submission deadline 16th. Okay, so that should be well underway as well. So a little tip, don't leave it to the last minute. Okay, we've extended a few of these deadlines. We can't keep doing that forever. We need to keep some sort of structure, and of course you don't want deadlines extending into your exam revision. So try to plan your time. If you've got a few days empty, do the assignment, even if it's not due the next day. Right? And the Power Amp labs are in the next 2 weeks. So right now you're still finishing the traditional mixer labs. Power Amp labs are going to be a brand new type of lab. So I'm going to talk about that a little bit at the end. There's going to be a lot of information coming on iLearn. You're going to operate the lab equipment remotely. Okay, so the idea is you don't need to come into these lab sessions. It's individual. You all log in. You can operate this tool remotely, and you'll be moving like switches in a physical system, right? So they're relays connected over the internet, and then you'll see actual output from the measurement tools there. So I'll give you a little bit more information there. It's the first time this lab's been done in Australia, I think. Okay, this type of technology has been used. So it's quite exciting, but also means there could be some issues along the way, so I'll warn you of that. Binesh has put a lot of work into trying to set it up, and we'll be asking for feedback at the end of that as well on how it went. But yeah, so the lab difficulty level shouldn't be too high, right? It's going to be fairly straightforward, but a little bit maybe confusing to set up, but we'll give you all the documents we can to make that easy. Okay, report writing tips. I know this is maybe a bit too late because I get a lot of emails asking some of these questions. I'm just going to summarize some tips here, and you can always update your report before submitting it. So my number one tip is to look at the marking rubric. Okay, that's given to you, that's on iLearn. So that gives you an idea of how the marks are weighted and what you need to do to achieve HD credit distinctions. So you can see where you focus your effort, okay? Don't put 100% of effort into making it look pretty if you need lots of effort in the results section, okay? So think about that sort of stuff. The best exercise you can do is like use that rubric, mark your own work. Imagine if you were the marker, right? Because it's some of your master's students will use master's PhD sometimes for marking. In this case, it will all be marked by me, but it's not much different. I'm still looking at the rubric. I'm looking at your work. I'm marking it. So do that, and you'll get an idea of maybe some things that are missing, right? You can add that in. Write a good abstract. Usually, any abstracts in these things are very often someone gives just a brief intro, right? An abstract is supposed to be a summary of the motivation, like why are you doing the work, why is it important, and the key findings, okay? So try to, in a very, very short section, just summarize that, okay? Use figures wisely. So 3 pages is not much space. It's going to be very difficult to fit it all in. You definitely can't put a picture of every circuit and a graph, individual data sets on each graph. So try to use multiple data sets on a plot where it's relevant and where it suits. Don't overcrowd your plots, okay? If it looks like a big mess, that's also bad. So you've got to be selective on what data you think is important and what shows your understanding, really, and evidence of the work. You don't need to provide every little bit of evidence to show you did every bit of the lab, because you have a lab mark, right? We can see that you were in the lab and did the work. I can check that. But this is about trying to concisely summarize that work. And don't forget things like captions on your figures, okay? So standard formatting, use just easy marks that you're going to lose. If you don't put a figure number, you don't put a brief description of what that figure means, then you're going to lose some marks in the formatting section, okay? And be concise, okay? So as I said, pick and choose the most important results, most important topics. You can cover a little bit of background, but don't rewrite the lecture slides or the worksheet. There's no need for that. What you're trying to do is demonstrate your understanding, all right? Show me or Binesh that you understood the topic, and that even if you were unsuccessful in one particular result, maybe you can offer some reasons as to why. That shows your understanding too, okay? So good writing in that results analysis sort of discussion section is key, okay? That's where you get that chance to really show you know what you're talking about. Okay, so that's midnight tonight, the deadline for that. So hopefully you've all finished it, or you're most of the way there, but maybe there's some tips that will just help push those marks up a little bit. Okay, so on to the actual topic of today's lecture. So this is lecture 1 on power amps, power amplifiers. So today we're going to we're going to introduce them, talk about design considerations, a bit of focus on classification, so how we class different power amps, and then we're going to focus on class A and class B. Next lecture we'll do class AB and a little bit on class C. Okay? So first, what kind of applications do we use power amps in? So of course now you've already done mixers, you've done differential amps. Most of this is using still low current, low power technology. At some point you need to have an output stage that drives some real world application. So a common requirement for power amps would be cell phones. So you need to communicate to a base station. You need significant power to do that, okay? Typically around a watt delivered to the antenna. So you need a power amp there. Audio systems, of course, if you want to drive a loudspeaker, you're going to need serious power for that. And microwaves as well, large power needed at microwave frequencies. There's many, many more, but those are just some common applications. So this is the final stage of your circuitry. You can have complex circuitry, differential amps, all sorts going on. The last stage, the output stage, is your power amp. So the design challenges. You need to be able to handle high power, naturally. It needs to handle high temperature, high efficiency, needs to be high efficiency and have low total harmonic distortion. Now, the temperature and efficiency ones are quite related, right? The reason you need to handle high temperature is because we're dealing with high power now. We have large currents going through our devices, right? So of course, if your device is 100% efficient, no problem, all of that power is going to be delivered straight through to the load. In reality, that's not likely to be the case, right? Which means that power that isn't going to the load is going to be absorbed somewhere and come out some other way. So that's typically through an increase in temperature, okay? So you need to be able to handle that high temperature. You've learned a little bit about how MOSFETs and BJTs work. They're semiconductor devices, right? They have a PN junction. That junction has a temperature where it will break down, it will be destroyed, okay? So maybe around 250 degrees C. It varies on your device. So the question here, would BJTs or MOSFETs typically be preferred for power amps? And we've got a bit of a mixture. So the answer there is BJTs, actually. So they can handle larger currents. That's a bit of a complicated topic because MOSFETs, a lot of modern MOSFETs can handle very high currents, but BJTs can handle them with better linearity. Okay, so high currents, you can still set up a BJT circuit to remain quite linear, and that's much more difficult with a MOSFET circuit. We won't go into that too much. We're just going to focus on BJTs. So nearly all the times when you see a power amplifier or you design one, it's going to be a BJT circuit. Okay, so large power delivery means large power consumption, and as I said, the devices heat up. You may notice that with your own cell phones heating up when they're trying to get some signal, when the power amplifier is working extra hard. So the performance parameters to focus on: efficiency, of course that's key, linearity, because otherwise we get distortion in our signal, and you can imagine we don't want that in our audio in our speaker. We don't want distortion in our transmission of our voice or anything like that. Distortion is going to corrupt it. And delivered power, that's the other main parameter. So you want to be able to deliver high power linearly and efficiently. Okay, those are the three key parameters. So the basic principles, so it's similar to just your standard BJT amplifiers that we would have looked at probably in the first section of this and also in ELEC375. But in this case, we're applying a large AC signal at the input. So our small signal models may not apply anymore. And you can see we can still have a bias condition. So we can still have our large VBE and then our signal makes our total VBE there. So we have a DC bias plus the AC signal. Now, as I said, it can be quite large. It can be large enough to actually switch the transistor off. So you need to carefully design it with some knowledge of what kind of output and what input and output signals you're going to have, so that it stays within the correct regions of operation. So how are they classified? So power amplifiers classified based on their conduction angle. Okay, so this is the amount of the AC cycle that the BJTs are conducting. Okay, so class A. What's the conduction angle of a class A? 360. Yep. So it's working at all points from 0 to 2 pi. Yep. Which is 360 degrees. So it's just in pi, it's just radians. Okay. So class B, 180. Yep. So this is only conducting half of the cycle. Of course, you can just put two class B amplifiers together to get the rest of that cycle, and we'll talk about that a little bit later. Class AB, yep, greater than 180, but less than 360, because then it would become a class A. Yep. So this is like a class B with some biasing, basically, to just shift it up a little bit. And again, you'll see why you need that later on. And class C. Yep. Okay. This one we're not going to cover in much detail. We'll cover a little bit of it in next lecture, but you'll see there are some uses for class C, particularly in radio. So A, B, and A and AB are the ones typically used for things like op amps and audio amplifier output stages. Okay, so they're the ones we're going to focus on here. And which one of these is likely to heat up the most when running? Class A, yep. So you can already see a potential downside of A. Like you look at it and think, okay, that's great, it's covering everything, but already you have this increased temperature you're likely to see with A, but we'll go into that in a little bit more detail. So Class A power amplifiers. Here's a typical Class A power amplifier circuit. So Q2 is used just to provide a constant bias current to Q1. Okay. We can see our output is going to be it's because it's just an emitter follower design. It's going to be V in over here minus VBE1. Okay, that gives us our output voltage there. So VBE1 will depend on the current, this IL drawn out, but that dependence is quite weak. Okay, so that means we can kind of ignore it, and we can assume that if VI increases, then Vout will linearly increase. So VBE1 will change with certain conditions, but most of the time we're going to assume it's constant. And that's where things like this diode come in handy. We have a VBE drop here, but as temperature changes in our circuit, it's going to also change for that diode, which will stabilize things so that it will remain the same voltage at the key points of the circuit. So you can add components like that just so that they work in parallel and ensure and reduce that temperature dependence, which is one of the key things for power amps. So, looking at the transfer characteristic, we see, so we have our V in on the X here and the V out on the Y. So we just see we have a simple one-to-one relationship there. And you can see there's a little offset. It doesn't go across to 0. That's your VB voltage, okay, your base emitter drop. Yep, so it just shifts things a little bit. We also have saturation. So this positive side saturation comes from the maintaining from the Q1 saturation point. So this is the VCC minus the VCE sat. Okay, so whatever that voltage is, often in a question that's given to you, might be 0.3 volts, something like that. might be, if it's not given, you can assume it's 0 typically, okay? And in which case your maximum, so your theoretical maximum, if you had this perfect transistor, would just be VCC. Yep. On the negative side, we can have it as the Q2 saturation, so same thing, the minus VCC plus the VCE set. But it may also be limited by the cutoff of Q1. So that's when if the full current I is going through RL, that would also cause Q1 to cut off and could be a limiting factor. So depending on your load resistor, that will change the negative cutoff. So if we want a full class A, if we want to use the maximum range of that output, then this is a condition that we want to meet to ensure that basically this line is matching or below this point, okay? So then you're really just limited by the transistor saturation, okay?
Sorry, can you mention again about the function of the Q3, the Q3?
Q3 here, the diode?
Yeah.
Yep. This is here, because this is setting a voltage here, right? Which is basically enabling your VBE. It's setting a voltage there. So that's mostly there, one, to set the voltage up and keep it constant, but also because it will change, its temperature dependence will be the same as for the transistor, because the transistor is just two diodes back to back, right, in the semiconductor layout. So as one of those temperature dependencies changes, so as this changes, the VBE required might change, but then the VBE supplied by this will change too to match that, okay? So it gets rid of the temperature dependence, simplifies everything. Again, we won't focus too much on that. It's just a standard of the design, but that's the purpose of it. Yeah. Okay, so yeah, that's our condition for like full class A maximum output range operation. So if we look at our output, we can swing anywhere between plus VCC and minus VCC. So our two supply rails. This is assuming a 0 for the VCE set, okay? So this is our output in the time domain. If we have a sine wave. Now if we're interested in power dissipation, of which will lead to our temperature rise in our transistors, that's going to be linked to the VCE of the transistor, okay? So the voltage from the collector to emitter that's dropped across that transistor, that's all going to go into your junction temperature, right? So that's VCC, this voltage, minus Vout, yep, straightforward. So if we plot that, knowing that our Vout can vary in accordance to this graph, then we see that our VCE1 can go from 0 to 2 VCC, okay? So the full width of the supply rails there. Again, assuming the saturation voltage is 0. Okay, so here we still have our VCE1 going from 0 to 2 VCC. So to work out our dissipated power, again, a pretty key thing for power amplifiers, we know the power equation, yep, so power is just your voltage times your current, okay, and this is the voltage we're interested in for the power dissipated in Q1, so VCE1, in this case times IC1, and again, the current, if we assume B2 is high, then IE1 is going to be almost the same current anyway, so that's the current essentially flowing through that transistor, so just timesing them together gives you the power. And the current can vary from I up to 2I down to 0. But notice the offset between these two graphs, okay? So when you're working out the actual power, you get this graph. So we see that the maximum is VCCI. And a big problem for the Class A amplifier, of course, is that the VCCI is when you have 0 input, okay? So you're getting high, what is it? Sorry, I'll wait for the next slide to go into that. But this is our instantaneous power dissipation, okay? Varying with time. Okay, so power dissipation, maximum power dissipation, VCCI, happens when V out is equal to 0, okay? So that's when we have no power going across the load, but a lot of power dropped across that transistor. It's going to heat up a lot. As you can imagine, that's a pretty natural state for things to be in. You might often not be running your loudspeaker, you might not be transmitting on your phone. So that's a lot of power that's going to be wasted and a lot of heat generated. And this is for the case when RL is equal to VCC over I, so that was our maximum output swing condition, okay, to make sure we got the class A full output. But essentially the power dissipation is going to depend on the load resistance, okay? So if we assume an open circuit, an infinite load resistance, maximum power dissipation in Q1 is then going to occur when V out is equal to minus VCC. Okay, and that's when your VCE1 is going to be equal to 2 VCC. So we get very high maximum power dissipation of 2 VCCI, but that's only the maximum, and the average is actually going to be just VCCI. Because that situation isn't likely to persist where you have where you have an open circuit. Okay, so that's this particular condition isn't likely to persist like the zero output one, so we don't worry about it too much, and we're more concerned there with the average condition. A bigger concern is if we have a short circuit at the output. Okay, if RL is 0. You're essentially going to try to provide an infinite current across the transistor. So you have very large current in Q1, which is going to lead to very large power dissipation. Okay? Heat up your junction and it will destroy it. So of course, a quick way to destroy a power amp without any extra protection would be to short that load. Okay? All right, we have a quick question on this. This is a fairly straightforward one. So find the power dissipated in Q1 under the quiescent condition. So that's just when V out is equal to 0, just that equilibrium state. You've got these parameters at the top there. 2 minutes. Okay, there's a hint on the screen in case you managed to forget the equation for power. Okay, everyone happy with that? So just to go through it. So we know the equation, as I said, is on the screen now, just here. Our VC1, if we have a 10 volt supply and 0 at the output, so it's going to equal just 10 volts, very simple. If we've got 0 voltage at the output, then IL is going to be 0, so there's going to be no current flowing through that resistor, which means our IE1 is going to equal I, and if we assume alpha is equal to 1, which again, if it's not stated, is fair, then that's also equal to IC1. So we have our current, we have our voltage, okay, being 10 volts times 100 milliamps equals 1 watt. Okay, so I think everyone got that right. That's a nice simple example. What about in Q2? Well, it's going to be the same result. So Q2 is just going to be, it's going to be negative and the current's going to be going the other direction, so it's still going to equal 1 watt. And it's a constant current of I by definition in Q2 there anyway. So you have the same power dissipated in this example in both Q1 and Q2. So your total power dissipation will be 2 watts, okay, across the whole system there. So power conversion efficiency, so this is of course a figure of merit for any amplifier, and typically you're going to want the efficiency to be high. That's just defined as your load power divided by your supply power, okay, so the power delivered to the load divided by the overall supply power. For power amps, this is always worked out using a sinusoidal output voltage, okay, because we're typically looking at AC in a power amp. So we can define that here with our V out hat. That's the peak voltage, okay, of our sinusoid. And our power, so we know power is equal to V squared over R. Yep, that's just Ohm's law change of the power equals I times V. Yep. And here our V squared term is V naught over root 2, because that's just how you get the RMS average, okay? So that should be familiar. And that becomes 1 over 2 V naught squared RL, okay? So that's your power delivered to your load. The power drawn by the supply, we just worked out, okay? It's just the VCC times I, and you have the two transistors in this case, so it's 2 VCCI. Yep, that's your total power. So you can just do one of these divided by the other, gets you your equation here for efficiency. So what are the maximum conditions? That's where it's useful to have this equation in this form, so of course these two are just equal. But we know that our V out cannot exceed VCC, and we know it can't exceed IRL. Okay, remember from that transfer characteristic we had the limits where we would typically try to make IRL equal to VCC anyway. So our maximum conditions are going to be when V out is equal to VCC, which is equal to IRL. Okay, you can see very straightforward that would make both of these brackets equal to 1, yeah, which means our efficiency is 1 over 4, so 25%, okay? So that's the best you can do with a Class A power amp, okay, a standard Class A. No, you can't do any better than that, okay? No changing the load or anything is going to improve it. So that's the best you can hope for, which obviously isn't great, okay? So it's not certainly not the most efficient amplifier design. So this is one of the negatives. You remember back to the waveforms, we knew it looked great because it does the 360 conduction angle, but it's not very efficient. And it uses a lot of power when it's at the quiescent state, the 0 input. Okay? So that means 75% of the power is heating up the transistors. Okay? All right, so we have another class exercise. So same parameters as before. If the output voltage is a 8-volt peak-to-peak sine wave, what is the power conversion efficiency? And I've got the equations up there to make that a bit easier. Okay, so a couple of different answers there. I'll go through that, but most people did get it right. It would be 16%. Okay, so let's just quickly go through it. Just following the equations that are on screen. So we have our PL. That's going to equal 8-volt peak squared divided by 2 times the 100 load resistor, so 200, which equals 0.32. Okay. PS just going to be equal to 2 times 10 times 0.1 amps, which equals 2. So our efficiency (0.16), which is 16%. Okay. So as a Class A power amp goes, that's not too bad, but generally it's not great. Okay. So now we have a look at Class B. Okay. Class B, you can see the design is a little bit different. This, in this case, we have a NPN transistor and a PNP. Okay, so we have QN and QP. So note that they are different transistors. It won't work if you have 2 NPNs or 2 PNPs. And if you're asked to draw one of these, it's a common mistake, people drawing the transistors wrong. Okay. So for positive input, QN is going to conduct and QP will be off. For a negative input, QP will conduct, QN will be off. Okay, it's a nice simple symmetry there. So one BJT is only on for half the cycle. Okay, this is Class B. So one of those is a each one of those transistors is essentially your class B 180 degree conduction angle. Yep. So this is what the transfer characteristic looks like. And you can see that there is a slight issue with class B amplifiers, and that is this section in the middle, okay? Because of course you need a certain voltage to turn that transistor on. So in the 0 state, it's good because both transistors are off when you've got no input, so you're not wasting a load of power in that common no input state. But it means you need to get that voltage to get the transistors to turn on, okay? So we have this dead band, so that would be around 0.5 up to 0.7, it all depends on your device, in both directions. And that results in something called crossover distortion, okay? So as your signal goes from positive to negative, that crossover point, it's going to be distorted. So for input voltages greater than 0.5, you get a nice linear output. And up to the saturation point, which, as before, is your power supply minus your VCE sat. So one thing to note as well, again, when you're doing exam questions and stuff, if you're asked to draw one of these, make sure you label every key point you can think of, okay? So you can see all the labels on here. You know, you're never going to lose marks in a question for adding an extra label that wasn't asked for, okay? So always label all those points, the saturation points, the dead band, things like that, okay? So what does that look like in the time domain? Well, that's our transfer function there. And in the time domain, we're going to get this little distortion effect around here every time we cross from negative to positive. So in a audio amplifier, that's going to make a very unpleasant sound that is definitely not what you want. So it would give you unwanted frequencies in the output. Okay, so you're going to have harmonic issues as well from this sudden change around there, and basically your output does not amplify the input with high fidelity. Okay, so any small voltages are basically just lost. Okay. So efficiency of a Class B amplifier. To calculate that, it would be quite complicated to always worry about that little distortion part, and as that's only for very small voltages and we're mostly dealing with large voltages, we ignore it, okay, for getting your overall efficiency. It's considered negligible, and that simplifies things quite a lot. So our power delivered to the load is the same as with Class A, okay, that's our average power across our load for the sinusoid, okay? So no change there. Average current taken from each of the supplies. This is going to be 1 over pi times the peak voltage divided by RL. So I'm not going to go into that too much here, but if you draw out those time domain signals, again, don't worry about the crossover distortion, then you can work out where the average of 1 over pi comes from, okay? So you can integrate over the sine curve, the half sine curve in this case, and then divide by the x-axis, which would be pi here, and that gets you your average. Okay, so if that's confusing to you, go away and draw out the curves and work out how that comes about. But that's your basic integration and averaging. And the power taken from each of the supplies is going to be the same. Okay, so this is your current. So your power is just times in by the voltage, and that's in each. The PS plus and the PS minus, okay? So total power is going to be 2 over pi times V peak over RL VCC. There's your total, okay? So it's that number and that number there that you're going to need for your efficiency. So in the simplest case, PL over PS is this equation here. You can simplify that down, obviously, because you've got a lot of the same terms. Pi over 4, V out peak over VCC. All right? So pretty straightforward to get to the efficiency there. So, quick question, this shouldn't take too long. What's the maximum efficiency of a Class B power amp? You got to vote. Okay, I think everybody's got that one. So yeah, if I show the other part of that equation, it becomes even more obvious. But yeah, so V out, if you set that to equal VCC, which is your maximum, again, assuming the VCE set is 0, then you just have pi over 4, okay, which is around 78.5%. Make sense to everybody? So straight away you can see Class B has a potential to be much, much more efficient than Class A. So a big advantage for Class B power amps, but it comes at the cost of this distortion, right? That's the penalty we pay for the higher efficiency when we're keeping our circuits as simple as a Class A or Class B. So the maximum power that you can deliver there can be found just by putting in the V out to VCC in the previous equations for the power. And our dissipated power, that's our power essentially that's going to be lost at heat if we're trying to calculate that. That's the power from the supply minus the power delivered to the load, okay? So it's the same equations we were just looking at for efficiency, but we're not dividing one by the other, we're just subtracting one from the other, okay? That gives you your dissipated power. If we're talking about the total dissipated power, then of course half of that is going to be dissipated in Qn, the other half in Qp, and therefore you need to make sure you've got transistors that are capable of dissipating half of that total PD, okay? And that's something you can get off your data sheet, and that's when you're designing your circuit, you can see how much power they can dissipate. So that PD over 2 sets a limit on the V out signal swing, so because your PD is going to depend on your V out. Worst case is this condition here. So 2 over pi VCC is going to be your V out set to your PD max. That's done through differentiation. We'll look at that in the next slide. So PD max, maximum dissipation, 2 times the power supply squared over pi squared over RL. And of course in one of the transistors it's just half that, okay? And that's worst case scenario, again ignoring VCE sat, for designing your amplifier and choosing your BJTs. So that's taken from, if we plot our equation for power dissipation, that's this equation here, plotted for every point for different V outs, okay? So that maximum power can be obtained by differentiating to get the point where the curve with the gradient is 0, yep? That's the peak, yep? And that gives you your PD max. So again, if you want to, you can go through all the maths of that separately, We're not going to focus on the maths here, but it's just differentiation to get that curve. And you can see right at the top of this curve, we have our peak in efficiency of VCC. This is the region we want to be operating in, where we have high efficiency, but also high output. Okay, if we're over here, then we have low output. We're not really. That's not what the power amp's designed to do. But we need to be cautious if any signals that we're putting in this region are close to our VCC, right? So they could saturate. So you need to be careful not to be operating too far along this curve, where you're going to get clipping as you get the VCC. Okay, so we've seen that in some of our previous labs. You can easily saturate with any amplifier, and it will just flatten your curve. So choosing exactly where you're going to operate is quite important. Okay, so we have a class exercise. For this class B output stage, VCC 6 volt, load resistor 4 ohms, outputs a sine wave of 4.5 volt peak amplitude. What's the efficiency at this output voltage? Okay, everybody happy? Voted? Oh, we've got some more coming in. I'll give you a few more seconds in case anyone else wants to vote. It changed. All good? So the correct answer is 59%. I'll just go over that. So we know that we are looking for get my pen to work. Our efficiency our PL over PS, yep, and we have the equations down here. PL in this case is going to be 4.5 squared over 8. That's 2 times the load resistor 4 equals 2.53 watts. Now PS, let's say plus, it's going to equal 4.5 times 6 over 4 times 3.141, that's just pi. .15 watts, and of course that's only for one of the PS's. Okay, so PS minus will be the same. We can say that PS is going to be equal to 2 times 2.15, 4.3. So meter 2.53, 4.3 equals 0.59, 59%. Okay, everyone happy with that? Someone's already voted. So next exercise on this, what is the peak current supplied by VI, assuming beta equals 50? So see if you can work that out. I'm going to give you a bit more time, see if anyone can get to an option other than the no idea one. This one's just a little bit less straightforward than the previous questions. We like to keep them all quite simple in the lectures, but just need to think about what's available to you in terms of the knowledge on the screen. Any more answers? Alright, that's quite a spread. Oh, okay. So everything got a vote except from the correct answer. So I'll go through that now. There we go. Fixed it. We need to lock these things. So let's have a look. So we're looking for the peak current supplied by your VI input, okay? Now, what is the peak current going to be in terms of transistors? Right, it's going to be, because we know only one's on at a time anyway, so it's just going to be IB, right? In terms of the, because we're talking about the input voltage here, so we've got the current IB. Yeah, that's what we're trying to work out here, the input current. Yeah. Now, the peak is going to be when we have the, obviously we know that our input current and a transistor, again, only one of these is on at a time, so we can treat it quite simply. We know IB is related to IC and IE, okay, just for your beta alpha terms. Yep. So when do we get the peak output? That's going to be when you've got your peak voltage across your resistor, right? Because if one transistor's off, then IL, IE of the one we're interested in is going to simply equal IL. Yep. So IE, let's say max, it's going to equal 4.5 divided by 4, 1.125. Okay? So that's maximum current at the output. Yep, at IE in this case. Coming here, yep. Then we just need to remember how all the currents relate to each other. So IB is equal to IE divided by 1 plus beta, okay? So that equals 1.125 divided by 51, 22.1 milliamps. Does that make sense to everybody? Yep. So that one, just have to think about it a little bit more in terms of what can you calculate, how do we get to that value, what's the question asking, all right? But once you know it, it's relatively simple to calculate. Okay, and finally, I'll just go through this one very quickly. So what's the maximum power that each transistor must be able to safely dissipate? So for that, we can just use our power equations, okay? So that one's going to be very straightforward. Six squared over pi squared times 4. .91. Okay. So in your questions, you could be asked to calculate any of these parameters or order them, or could be more of a design question if you're given some certain conditions, like a transistor that can take this much power. How do you design it to not overheat in these conditions? Okay, so you might need to think about it in terms of how you approach that. Okay, so just a quick note on methods to reduce the crossover distortion. So you can actually use an op-amp and negative feedback. Okay, so a high gain op-amp here, negative feedback taken right from the Vout output. That can limit your deadband, and it will change it from 0.5 volts to 0.5 divided by the gain of that, the open loop gain of that op-amp, okay? So you can reduce it to a very small amount of crossover distortion. Of course, that's complicated your circuit. It's also limiting your frequency response a little bit, because your slew rate of the op-amp is likely to be slower than the response of your transistors, okay? So then if you're on high frequency applications, the slew rate of the op-amp might become an issue, okay? So an alternative to this is one way to do it, but an alternative is to go to the class AB, which we'll be discussing more next week. I'll show it briefly here. We also can operate these from a single supply, and again we could ask you questions where you just have a single supply. So here we just have, for ease of the calculations and the formulas, we'll notate it as 2 VCC to ground, okay? Because it doesn't matter too much, because a lot of the stuff is about biasing it to the right point in the middle. But you would need, in this case, a capacitor for your coupling here, okay? Because you want to remove that bias, that DC point. So those are just add-ons to a standard Class B that you can consider. And just to introduce you, we're not going to cover it today. We'll probably finish quite early today. Class AB, you can see, quite a similar structure to your Class B, but we've added some biasing, okay? So small fixed biases, we can reduce the crossover distortion, okay? But this does mean some current's going to flow through the BJT even when the input is 0, okay? So there's always this trade-off between having really high efficiency and low power dissipation under that 0 condition, or having no crossover distortion, okay? But here the transistors conduct for a very small input voltage, crossover distortion almost gone completely. So we're going to focus on that one next week and introduce a little bit on C. The Class AB will be a bit more complicated because we can talk about the different ways you bias it and what that means. I want to remind you all again, some of you missed the beginning, the upcoming assessment tasks. So lab report 1, end of today. Yep. Hopefully you've all nearly got it done. Assignment 3 is going to be next week, which again, hopefully you've made a start on that. And the power amp labs, so we have a couple of slides to just detail what they'll be. So this is lab 4, or lab module 4, running in week 10 and 11, so next week and the one after. As I said, you won't need to physically come in to your 3-hour lab time slot. You'll be able to access all of the hardware using just your Chrome browser and a laptop, PC, tablet, whatever you want. What we will have is the tutors will be available, and probably myself or Binesh in the lab for at least 1 hour during one of those time slots, so we'll tell you when. That's just for optional consultation if you're struggling with anything. Of course, we're always also on email. We also encourage you to use the forums, because if there's some connectivity issue, someone might have solved it quickly, you could just post that. Another student might be able to help you quicker than we get to you. If 1 hour is not enough, we'll try to do that early on in the week, and if it's busy, then we'll just be there for another hour on the Friday or something as well. So we can adapt there, but it's not mandatory, so up to you if you need it or not. It's individual, don't work in your pairs. A worksheet's going to be provided, detailed instructions, how to do your pre-lab. It's going to be a Turnitin submission of this worksheet, basically, so you can have some things you work out and write as you go. Yep.
Do you have a time limit to complete the lab?
There'll be it will be within the 2 weeks, basically. There'll be a deadline, so that would all be posted on the worksheet.
We can do whenever.
But it will be flexible timing, so you don't need to do it during the 3-hour slot. You have basically the week or whatever to do it. So it really should hopefully make things easier for you guys. You've got complete flexibility, but don't leave it to the last second, because all students do that. So the end of week 11 is when you upload that filled-in worksheet. It says like a report, but you won't be writing it up like a report. You'll just be filling in this worksheet. Okay? What we can do through this, and part of the assessment, and the way we know you're doing it individually, is every click and everything you do is logged, right? So we know when you're logging in and when you're doing it. There's going to be some interesting stats as we see all those logins come right at the end. But also we're going to know if you submit something and we saw you never logged into the system, we know you just copied somebody's work, all right? So there is an element of tracking. So don't try to get around it or be lazy. Just do the work and log in. I don't think it's going to be very difficult. Binesh did most of the design, so I haven't looked through it all yet. But as it's the first one we're running, it won't be crazy sophisticated. So that's just an idea. This is the hardware. This sits in our office. So as you do stuff, there's going to be little switches going off in here, and it sort of multiplexes that so multiple people can do it at the same time. You just log in and it should be all nice and seamless. And that's some sort of snapshot of the kind of interface you're going to see in this virtual lab. And so you make these connections between switches. We have these circuit boards already in there that will connect up, and you'll get to see the output characteristics that result. So another bonus of this is hopefully there won't be this whole, like, you can't put the transistor in the wrong way around, you can't have a dodgy connection, because they're all done and tested. Okay, so yeah, we have function generators in there, 4-channel oscilloscopes, variable resistors, switches, wires. So it should be quite an interesting lab. As I said, you're the first people in, I believe, all of Australia, definitely the first in Macquarie, to try this. So we'll see how it goes. All right. How does the idea sound to you? Do you like the concept? Yeah? Okay. So we'll be interested to hear the feedback, see if you're still happy afterwards. But yeah, so hopefully that goes well. But that's everything for today. So keep an eye on iLearn for all the updates on that. Yeah. And we'll send out announcements.
The grading will come with the worksheet, similar to the ones we have.
There'll be an indication on how you get the grades. Yeah, I'll make sure.